All right, section 10.2, we're going to talk about the kinetic-molecular theory. So what we did in 10.1 is we kind of wrapped up all our equations that we learned about gases. In 10.2, we're going to review the kinetic-molecular theory and how we can how we actually get those equations and how something like the ideal gas equation actually works. So remember, the kinetic-molecular theory is establishing how an ideal gas works. So this is our understanding of what happens to gas particles in a container or in an environment as things change. So there are 5 assumptions of the kinetic molecular theory. We're going to go through each one of the 5. So the first assumption in the kinetic molecular theory: gases consist of large number of molecules that are in continuous random motion. Makes complete sense. Gas molecules are large, they're in complete random motion, or continuous random motion, excuse me. Assumption number 2, the volume of all the molecules of the gas is negligible relative to the total volume in which the gas is contained. And what that law is saying is, since a gas expands to fill its container, the volume of the gas doesn't matter, it's the volume of the container that matters. Since a gas fills the space of its container, it's the volume of the container that matters. Assumption number 3, attractive and repulsive forces between gas molecules are negligible, which means that they're really not going to collide, all right? Or the containers, actually, I shouldn't say they're not going to collide. The collisions are what we would call, from a physics standpoint, inelastic, which means that the energy lost or gained is negligible. Assumption number 4 of the kinetic molecular theory is that when we do have collisions, right, energy is being transferred. The average kinetic energy of this sample is the temperature. So the average kinetic energy of the molecules is typically how we get temperature. So if you're defining temperature, the average kinetic energy of a sample of a gas is defined as temperature. So that's kind of the 4th idea of the kinetic molecular theory. And lastly, we kind of summed it up. 4 and 5 I kind of summed together into 1. The average kinetic energy of molecules is proportional to the absolute temperature. So the average kinetic energy of a sample is equal to the pressure of the gas. So those 5 things, kind of make sure that you're aware of them. Gases are in continuous random motion. The volume of the container is what matters. Collisions are what we call inelastic. And the average kinetic energy of a sample is what we call temperature. 2 things to talk about when we talk about gases: we have effusion and diffusion. We've talked about diffusion. We have not covered effusion. Effusion is the escape of a gas through a tiny hole in an evacuated space. So like a balloon, even though a balloon holds gas, why does a balloon deflate? Because there are very, very small, tiny openings in the surface of a balloon that over time allows the molecules to escape. Now if we think about this, which are going to escape better through a small hole? Small molecules or large molecules? Think of it this way. You have to, all right, you're outside in the baseball field and molecules are either golf balls or softballs. Which one can fit through that chain fence very easily? Right? Most typically, golf balls. The smaller molecules can fit through faster and more efficiently rather than the larger molecules. So that's an example here. If you have a balloon filled with argon and a balloon filled with helium, which molecule is smaller? Helium, proving why a helium balloon is going to deflate faster. All right, it's going to fit through those tiny openings in the balloon, and we're talking very, very microscopic tiny openings. So that's effusion. Diffusion is just the spread of a substance throughout space, the random movement of a substance throughout space. So you can see here, if we follow a particle, it's the random movement of that particle throughout the space. Now, to figure out diffusion, or the kinetic energy of a sample, the kinetic energy of the first sample is always equal to the kinetic energy of the second sample. So kind of keep that in mind. If we have to use Graham's law ever to solve something, Ke1 is equal to Ke2. Now remember, kinetic energy is equal to 1/2 mv squared. So 1/2 m1v1 squared is equal to 1/2 m2v2 squared. That is just setting the kinetic energies of the sample together, or equal to one another. And you can rearrange that equation all that you like. They do it 100 ways there, but all that you have to do is KE1 is equal to KE2. In my opinion, that's the easiest way to do it. Now, when we talk about ideal gases in a real world, the behavior of gases, this ideal gas equation that we've been focusing on, only really holds true at high temperatures and low pressures. So high temperatures and low pressures does the ideal gas actually hold true? What happens if we flip-flop and go high pressure, what if we go high pressure and low temperature? What happens if we do that? You're going to see that gases start to behave wildly different. So here's a couple of examples. Remember, I'm going to go back to the last slide again. An ideal gas is high temperature and low pressure. High temperature, low pressure. If we change those, we're going to get more of a real gas instead of an ideal gas. So if we just look at high pressure and different temperatures, we can see that gases behave differently rather than ideally. And this assumption of the ideal kinetic or ideal gas laws really break down when we have high pressure and low temperature. And what they do to correct for this non-ideal behavior is there's a law called van der Waals equation. It looks like this. Don't worry about this. We're not going to cover van der Waals equation in great detail. So just to give you an idea, the van der Waals equation fits real gases much better than the ideal gas equation does, because then, again, remember, ideal gases are high temperatures and low pressures. So kind of keep that in mind when we talk about ideal gases. They really only hold true at high temperatures and low pressures. So when we talk about ideal gases, we have to talk about the kinetic-molecular theory. We have to talk about how they act through effusion and diffusion. And then we have to talk about how real gases actually act and what are the assumptions that we are making for temperature and pressure when we talk about an ideal gas. But that concludes Chapter 10, and this also concludes Section 10.2.